Quantum physics. Sometimes light behaves like waves, and sometimes light behaves like particles. Sometimes matter behaves like waves, and sometimes matter behaves like particles. What is going on here? Well, quantum physics unites these two concepts here. And I'm going to try to explain to you what modern-day physicists believe happen when you're dealing with light and matter, and how it sometimes behaves like a wave, sometimes it behaves like a particle. Okay? So, here we go. Basically, this is what physicists believe. Okay. If a particle or wave or whatever it is you want to call it is not being watched, it's kind of like in a blur. One arm? Two arms? It's kind of like in a blur state, where it's kind of like all those places there at the same time. So basically something like an electron, when you're not looking at it, it's kind of like in a blur state. And this is when not being watched. But as soon as you observe it, as soon as you watch it, as soon as you try to take a measurement on it, this blur state collapses, and the electron becomes the electron that we know and love as a particle. And then if you look away, if you weren't watching the electron again, or the particle, or whatever it is, it would go back to the blur state, and then when you look at it again, it would snap back into position, and like 99 times out of 100, you would find it, like right here. But sometimes, if you don't look, and the electron goes back into that blur state, and then you quickly turn and you look and you watch it again, sometimes it might pop into existence, not where it was, but maybe like over here. And then you don't look at it, you turn your back, it goes back into that blur state, and then when you look at it, it snaps back into existence, but maybe this time it snaps back into existence over here. Most of the time, when you go to observe it or look at it, where does it snap into position? Right here. So, basically, another way of drawing this is to show a probability wave. It's statistics. And it kind of goes like this. If you have like a gold nucleus, or an alpha particle, or an electron, yes, it basically is in a blur in this area right here. But we draw a probability wave that starts off low and gets high. Should be symmetrical. Try that again. And basically, where this probability wave has a big amplitude, that's basically where you're most likely to find the electron, or basically where the electron will pop into existence when it's being observed. So basically, if you observe the electron, where will you most likely find it? Right here. But if you look away and then you look back again, you'd probably find it here again. But on a rare occasion, you might find it out here. And you cannot predict exactly where the electron will pop in or form. It's just totally based on statistics. So if you have, like, let's say a light particle, and let's say the light particle is moving this way, you never can be exactly sure where the light particle actually is. But when observed, you know where you have the highest probability of finding it. So this black wave right there is called a probability wave. The probability wave's amplitude, height of the wave, indicates where you have the highest chance of seeing the electron if you observe it or if you look at it. Now, Einstein started this whole thing with the photoelectric effect, and he conclusively showed that light, which was known to behave as if it's made up of waves, he conclusively showed that it was behaving as if it was made up of particles. Well, as the physics developed all the way to this, quantum physics, Einstein did not buy into this. He has a famous quote he said, God does not play dice. Meaning, Einstein did not like the whole idea that no one knew exactly where the electron was, and it was always a matter of probability where you would find it. But this quantum physics is probably the most studied and tested scientific theory there is. And basically every single experiment ever done to test this has worked. I want to share with you just one of many experiments that show this sort of thing in action. Here's the experiment. Imagine if you have a lead container with super thick walls. And inside this lead container, you put an alpha particle, a helium nucleus. Yes? You put it inside. Maybe there's a little tiny door. You can open the door. You put the alpha particle on the inside. An alpha particle has a charge of +2 elementary charges. Has a mass number of 4, because it's made up of 2 protons, 2 neutrons. So it probably has like 8,000 times more mass than an electron. Well, according to quantum physics, when you're not observing that alpha particle, it's in this blur, this quasi-waveform state. And you could look at a statistical wave which would show you where you have the highest probability of finding it if you look to see it. So let's go ahead and draw in the probability wave for this alpha particle. Again, that should be symmetrical, not perfect though. So, when physicists go back and take a look to see where the alpha particle is, most times they find the alpha particle inside the lead container. They open the door and they find it. Oh, there it is. You know, just where we left it. Closed container, still in there. Check again. Where is it? In the container. Close the door. Go back later. Check again. Where is it? Okay. Now remember, that alpha particle cannot penetrate the lead wall. There's no way an alpha particle can actually penetrate and actually make it through a lead wall. Again, this has been shown conclusively over and over again. Guess where the alpha particle, on rare occasions, but it's been documented, shown over and over again. Guess where the alpha particle has been found on occasion? Outside the wall. Look at the probability wave over here. Do you see it right over there? It's small. It's not as big in the middle, but there is a chance that you'll find that apple particle outside the wall. They actually have found it outside the wall. This whole process is called tunneling. And it's a repeatable scientific experiment. Let's go occasions, right? 2 C's. Sometimes, on rare occasions, the alpha particle and this whole process is called tunneling. Now, some physicists say that this only works for things that are really, really small at the atomic scale. Other physicists say, hey, no matter how big of a particle we test this, it has never failed. And they keep on testing this with bigger, more massive particles. Some physicists take this really seriously, and they think that when you're not looking at the door, if no one is observing the door or taking measurements on the door is in a blur-like state. And then when you go to look at it, it snaps into its current state. I'm constantly trying to see if I can see the blur. And it brings back meaning to that age-old question, which I used to think is the silliest of questions. If a tree falls in the forest, does anyone hear it? And the question is, if there isn't anything observing it, would anything actually even see it or hear it? Again, very, very mysterious, spooky stuff. This ultimately led to the Heisenberg uncertainty principle. Which states you can never really know two exact things simultaneously about a particle. The two things that you cannot know precisely at the same time are the particle's speed and the particle's position. So let's say that there's a particle, and the particle is moving through like here. If you do experiments to try to see where the particle is at a given instant of time, you can keep narrowing down and getting more and more precise measurements of where it exactly is at a certain instant of time. But when you do that, you become less able to obtain how fast the particle is going. On the other hand, if you do experiments to try to test how fast the particle is going, then the more you know, the more precise your measurements are about how fast the particle is going, the less you know about where the particle is. So, the particle's position and momentum. Momentum, of course, is related to the speed. The particle's position and momentum cannot both be if you zone in and try to figure out where it is, the more you zone in to see where it is, the less you know about how fast it's going. If you zone in to try to see how fast it's going, then the less you know about where it is. The more precise object's position is known, then the less precise the object's momentum is known. And vice versa. Vice versa. The more precise the object's position is known, the less precise the object's momentum is known. And the more precise the object's momentum is known, then the less precise the object's momentum is known. Say you have a particle, and let's say this is 0, and this is 1, and this is 2, and this is 3, and these are meters. And let's say there's a particle, and the particle is moving through, and you try to take a quick measurement. And let's say you are confident that you know that the position of the particle at a certain t time is between 1.5 and 2.5. So you could record the position of that particle like this. It's at the 2 meter mark, plus or minus. Well, if you're sure it's between 1.5 and 2.5, what will be the plus or minus? 0.5. This right here is the uncertainty in the position. Let's say that you do experiments and you find that right at that key point right there, the velocity is between, let's say, 50 and 56 meters per second. At that given location. So then you could say its velocity is 53 meters per second plus or minus 3 meters per second. Well, I want to take out that other meter per second. 53 plus or minus 3 meters per second. So this little piece here is the uncertainty in the position. This little piece here, that's the uncertainty in the velocity. And to give it direction, we'll say positive. Now, let's say the mass of the particle is 0.02 kilograms. If the mass of the particle is 0.02 kilograms, then what can we say is the momentum? I'm running out of space here, so I'm going to just squeeze it over here. Not the best board management here. But I could say that the momentum, we know, is equal to the mass times the velocity. So basically, it's going to be 0.02 kilograms so basically, we know that the momentum is between, this is going to be 100 kilogram meters per second.
Isn't it 1?
Oh, yes. Because the point, right? So it's going to be between 1. I can't write it up there. That's just not enough room. Come back over here. Momentum is between 1 kilogram meter per second when you multiply the mass times velocity, and what's the other one? 1. What's 56 times 0.12? 1.12? So we could say that the momentum equals 1.06 plus or minus what? 0.06. And this here is the uncertainty in the momentum. Well, if we tried to do new experiments to zone in better on the position, and if we got this value here to decrease, to go in smaller, so we knew more precisely where it was, well then guess what would happen to the value of this guy over here? It would increase, it would be bigger. The more we know for certain about the position, the less we know about the momentum, and vice versa. And what Heisenberg actually showed was basically the uncertainty in the momentum times the uncertainty in the position is always greater than or equal to Planck's constant over 2 pi. It's not just an engineering thing. It's a law of nature. You can never get those two things smaller than h over 2 pi, where h is Planck's constant, delta P is the uncertainty in the momentum, and delta X is the uncertainty in the position. The more you know about one, the less you know about the other.